Okay, good afternoon and welcome to MAE 209. My name is Richard Kohar and this is lecture 15. So, in this lecture, we've going to start chapter 4 of the textbook. And chapter 4 concerns itself with a different case of random variables. So hopefully, let me just check to make sure. Make sure I'll check in the chat to make sure that everyone can hear me. So we have today's lecture 15. Oh, excellent. So people can hear me okay. So we're covering probability density functions. Oops. Okay, so just so this is what we're covering today's 4.1. So in chapter 3, we looked at the discrete case. So, what I'll do is just to answer some questions and not to interrupt the flow of kind of our topic. So, yes, I should announce that we're going to have a quiz. 2 is on Thursday. And it will cover up to section 4.1. So that's today's class. The questions are posted. They're posted on Moodle. As well as it will still be virtual. It will be open book. And someone was asking about the poll results. So it was approximately 70%. Drum roll. We're in favor of continuing the class as is. So we're going to have online lectures, so you can still watch them on YouTube. So online lectures, and the only thing that will be slightly different is that on the Thursdays when there are exams, we'll have to have that in person. But in-person exams, and that's not quiz 2. So not this Thursday. Okay? So I'll keep these announcements, and that will be posted with my lecture notes as well. So, okay. Okay, so does that answer the questions in the chat? Think so? Excellent. Okay, so when we had discrete, let's kind of cover some of their. We talked about the PMF, or the probability mass function. We talked about things such as the CDF. We talked about expected value. So when we had, say, these were kind of like the probability of x equaling x. We had the probability that x is less than or equal to x. We had expected value, which was the sum of all the possible x's. So we had the, it was the sum of the x times its associated probability. Are there any calculators you won't be accepting in person? Oh, that's a good, well, calculators should be fairly something like this. Should be like something similar to this Casio that I have here. So there's like a Casio. This is kind of what I'm thinking of. Casio FX 991MS, something like that. They should be, they're non-programmable. And non-graphing. So if you show up with something that has the textbook programmed into it, or you can use Python. I've seen calculators now that have Python built into it, and you show up with a graphing calculator, that's something that's not acceptable. We're expecting something, where you can use to do, your basic scientific calculator with you can have your trig functions and your exponential functions, and you can do multiplications and additions and stuff like that. But graphing, doing anything where it's kind of more complicated than that, no. Okay. We also had to say the variance. Oh, and we don't use E, we're going to use V. And then we covered kind of special distributions. So what were the ones that we covered? Well, we covered the binomial distribution. Again, you have to remember your assumptions. There's the three assumptions that the trials, well, first that there's two outcomes. That there's a success and a failure. That the trials themselves are independent, and that the trials are identical, meaning that the trials are not changing from one to the next. We talked about the hypergeometric distribution. we talked about the negative binomial distribution. And so these two were related to the binomial distribution. We had the negative binomial distribution was the number of failures that you would have when you had the rth success. And lastly, we talked about the Poisson distribution. And why was that important was, again, we could use the binomial distribution to approximate the Poisson distribution. And one thing that I should mention that when we covered it, when we were doing the approximation, that you can approximate the binomial distribution with the Poisson. And this is with the rule of thumb. So with this rule of thumb, you can say that the trials is greater than 50, and that they combined the multiplication of the trials with the probability is less than 5. So again, we usually use Poisson distribution for rare events occurring, that the probability is usually quite small and that the number of trials is quite big. Okay, so we covered discrete, and that's chapter 3. And in chapter 4, so we'll say that this is chapter 3. So then when we talk about continuous, we don't have a PMF anymore. Instead, what we have is we replace it, instead of kind of a function defined on discrete points, now we have to start thinking about things over intervals. So we're not defining it on points anymore, intervals. So instead of a PMF, we have what we'll call as a PDF. Now don't get too worried about all the rest of the terms here. And there's a PDF, and they'll usually use f of x. We'll have a CDF, and so they'll use a capital letter now. They'll use a capital letter F. When we get to the expected value, we're not summing over discrete values anymore now. Instead, we integrate. And so that's kind of the jump, really, is instead of using functions that are defined on points, we'll have continuous functions. And instead of using summations, we use integration. So hopefully everyone remembers their, oops, I should use my f of x, because it's the x times the PDF. I guess there was something in the chat that I didn't quite see, but thank you for taking care of that. Hopefully there wasn't anything too inappropriate. But if there was, I apologize. I didn't see that. So the variance, again, works the same way. You can use that same formula again using the expected value. And of course, there'll be some special distributions. So instead of them being defined for, for points, we're going to be describing those with continuous functions. So instead, these are continuous functions. It was a spam bot. Okay. So hopefully that gives you an idea of where we're going with this, kind of a roadmap. And we'll, basically we'll do what we did in chapter 3, except now we're working with a continuous case. So we'll be involving some integrals, and there will be some special distributions that we see. Again, we can describe certain situations like that. Now, I guess I should make a couple of comments again, because we're in this class that everyone is either an engineering student or a science student, and they'll probably be working in the real world with some real world applications. So I'll make a little comment about that. Let's say that x is a continuous if we say that it's a continuous random variable, so it's a continuous random variable if its values comprise of so again, we're talking about the values that this can take on. So what those little the little x's, what all those possible little x's could be, right, for that big X. So for that one, the values comprise of a single interval on the real line. So I'll use notation like, this is like a closed interval, say A, B on the real numbers. So a subset of the reals. You could have a union of disjoint sets. Disjoint set of intervals. On the reals. And again, a union of disjoint sets. And basically that means that they're non-overlapping. Okay. And the second thing is that the probability of, I'll use a capital X here, equals some constant, let's say C is equal to 0, and that's for all possible values of C. Okay, so again, that's what's different than from the PDF, the PMF. From the discrete case. Okay. So let's just say here's some examples of some continuous random variables. So the first one we can use is, in the textbook they said like depth of a lake. where the interval would be, say, A to B, and that's the minimum depth of the lake. Oops. And over here, that would be the maximum. So let's say number 2. Something that we might be a little bit more familiar with is, say, the pH of a solution. So again, pH is how many hydronium ions are in the solution. And again, thinking back to our first year chemistry course, that the value then would be that those values X is from, well, you can have from 0 to 14. Okay. So that would be like the minimum value that you could have for a pH solution, and this could be the that's the maximum. And again, that's the more you go to 0, the more acidic; the more you go to 14, the more basic. So while let me just finish that off. So just as a small remark. While most of our measurements are discrete by nature, so discrete measurements, and those are due to the amount of precision that we have with our instruments. Amount of precision by the instruments. So, why we use continuous random variables? We use continuous random variables because well, first of all, they approximate the real world well. And it makes it easier to analyze analytically, so the calculations. So analytical. Okay. Now, going back to each of these, again, when we think about, say, the depth of the lake or the pH of a solution, we can't say, like, because of condition 2 here, again, that X is a continuous random variable, because we can't just say that what's the probability that the solution is 7.5. We know what that probability is. That probability, if it's, again, assuming that it's a continuous random variable, will equal 0. Okay. And so again, so when we switch to using a continuous random variable, so going using our previous examples, So if we use our previous example, number 1, say the probability that x equals, say, 50 meters, well, we know that would equal 0. And for number 2, if we thought about the pH of a solution, what's the probability that the pH equals 7.5? We know that would equal 0. So what we need to now think of is we need to be thinking not in terms of points, like say 50 or 7.5, but instead we need to be thinking about intervals. So again, these are points. And if we think then over here, this would make more sense, is what's the probability that the lake is between, that the point that we're sampling is between 50 and say maybe 60? Or what's the probability that the solution is between say 7 and 8? So now instead we're thinking, instead of points, we're thinking of intervals. So let me just define then. Let's say that let x be a continuous random variable. And so this is where I'm starting to define a probability density function. And we'll say, and f of x be the PDF, the probability density function. That's the PDF of x. Okay. Then the probability that the value of the random variable x is little x on the interval a to b is given by, so we have the probability from a to b, so it's the probability that a is less than, so this is the random variable is between a and b. So instead of using the summation, say from a to b, we're going to use the the integral. So it's the integral from a to b of the probability density function f. And because it's we're integrating, we need our dx. So this is important. And now it should become a little bit more clear now why we can't integrate on a point, why the probability is 0. So if we let a equal b, then again the probability is x is equal to a. That means that we're integrating from a to a, and that's one of our rules that we knew from our integration. of the definite integral. And everyone in the chat, what's the value when I integrate a function from a to a? Regardless of what that value of a is. Good. Yes, it's equal to 0. So again, that's why we have that second condition. Perfect. Yeah. So again, when we're thinking of continuous random variables, we're not thinking about points anymore, but we're thinking about intervals. So I'll put this in red. Oops. Okay. Now, just like how we did in the discrete case, there are conditions that we need for the PDF, or the probability density function. So for f of x to be a probability density function, it must satisfy two conditions. So the first one was that the function must be non-negative for all the values of x. So again, it can be positive or 0. And the second condition is that if we integrate over, say, the entire real line, so again, when we think back to our discrete case, when we summed up all the values of the probability mass function, we wanted them to equal 1. So in the case of where we have the continuous function, when we integrate over the entire real line, we want this to equal 1 as well. So you can think of this that the function, say like this is a function f of x, that if I integrate over the entire real line, we look at the area under the curve, is equal to 1. Oh, sorry. Someone wrote if. Oh. Sorry. That's if we. So if we let a equal b, then. Okay, excellent. So what we'll do now is we'll look at let's use a uniform distribution. So let's use a uniform distribution as our first example. So we'll say that x is a uniformly distributed random variable on the interval a, b, if the probability density function of x is given by we'll do 1 over b minus a, and that's if that x is in between that on that interval, and we'll say it's 0 otherwise. So let me just kind of give you a little sketch. I'm not sure if it has it in the textbook, so I might as well show you what it should look like in general. Something like this. So we'll have f of x, and here's x down here. We'll have our 2 points. We'll have a, we'll have b over here. It'll be some sort of flat line, and its value would be 1 over b minus a. Okay. And using our definition, what we had from our, say here, let's say that I picked some values inside of it. Say I used, let me say I use C and D, something inside of there. Then if I did the probability, say from C less than X less than D, well then what I'm doing is I'm integrating from C to D of f of x dx. And so, because it's just the same thing, what we get is D minus C. Oh, did I make a mistake? I might have. D minus C, and what else do I need to include on this as well? Remember, we're calculating the area under the curve. So I have, this is basically, essentially, I've done a box. There we are. Yes, exactly. So there's our our width and we need our length of the box. So we'll also need to multiply that by 1 over b minus a. Okay. So let's just do a couple of examples. Yeah, so you can think of this as, oops, didn't mean to have all the pens fall. But here we need this right here. And up top here, again, I'm just color coding this. There we go. So here's our example. Let's say that x is uniform, random variable, over the interval 0 to 10. Let's calculate the probability that x is less than 6. Okay. So what do you think it is in the chat? X is less than 6. Six-tenth. Do we need f of x? Yeah. Well, I've told you. So that with the fact that I told you that x is uniform random variable over x from the 0 to 10, you should be able to figure out what that PDF is. Again, because we just go back up here. So using that, the PDF should be 1 over, so we have b is 10 minus 0. So I'm just left with 1 over 10. That's if x is on that interval from a to b, and 0 otherwise. So integrating this, I have a constant, so I have from 1, I have 1/10 x from x equals 0 to x equals 6. So I get 1/10, and then I'll have 6 minus 0, so that gives me 6/10. Or 0.06, good. What's the probability that x is greater than 6? Yeah, you can do it that way. Yeah, in the chat they've taken the compliment. I'll choose to write it like this. We'll go from a 6 to the end of the interval, which is 10. So again, I have 1/10 x from 6 to 10. So 1/10, 10 minus 6. So that gives me 4 or 4/10. And lastly, we have, say, something like from 5, and let's throw a curve in here. Let's do to 11. So the way that I would do that is I might have to break this up into two integrals. And the reason for that is going from 5, well, it's defined. And now it's for 0 to 10. So I know that I can do my integral of the PDF from 5 to 10. So that's 1/10 dx plus, and then I need to do my integral from 10 to 11. And the value of the PDF is 0, so I don't have to worry about that. So integrating that, I'm left with 1/10, 10 minus 5, or 5/10. Okay, so is there any questions before we finish for today? There are problems posted online, so again, check that out on Moodle. And of course, if you had clicked on the link from Moodle to get to the YouTube page, you would have seen that there's some questions posted. So again, just as a reminder, we have our quiz on Thursday. It will cover up to section 4.1. The exercises are posted on Moodle. It'll be virtual and open book. Is there any other questions? Okay. Thank you, everyone, and I'll see you on Thursday. Take care. No, it'll be during the first period, similar to last time. Yep. I'll put that down. Okay. Take care, everyone.